Hello everyone, I am Dr. Satyanarayan Rao. Currently I am working with some sensor data from a place called Berambadi watershed. It's in Karnataka, and if you are more interested about this place you can visit this website I'm showing here. In this video what we will do is that I'm not going to go into the actual data, but I just want to talk about what we can do if we have this kind of time series data. So here you can see actually the setup for our data set. What we have is that the data is from a single location where we had sensors at two different soil depth, one at 5 centimeter and another at 50 centimeter. And these sensors actually measured soil moisture and also electrical properties like the electrical conductivity. In the earlier years and in the later year it was tuned to measure dielectric properties. And we also had a nearby weather station that actually was taking care of the precipitation data. And in this video, actually, I'm not actually going to analyze the data or show any results or show any of the data. So the idea is just to walk you through the workflow that I will follow if I wanted to do something like calculate soil infiltration rate or explore rainfall soil moisture dynamics. So I will more talk about how to define rainfall events, set up the analysis window, and use basic time series techniques like cross correlation. This kind of workflow at some stage will accompany our data paper, and we will also include a lot of other small exercises. For now, let's see how we can define the rainfall events. So in this slide, we will see what is the infiltration in this context before we go into the workflow. So when it actually rains, water hits the ground and the surface actually immediately gets wet, the top layer of the soil. So that's why we have a sensor at the 5th centimeter. And that water actually takes some time to go to 50 centimeter. And there are a lot of things that can happen in the way, like the plant roots can take up water before it reaches 50 centimeter and it can throw out as a evapotranspiration, or it can also evaporate from the surface, or even the water can just drain away sideways like runoff. So not all water that touches the 5 centimeter will actually reach 50 centimeter, and even if it reaches, it takes certain time. And the idea is that we will see how we can quantify that time it takes to reach 50 centimeter. You might ask, if it is in the single location, the data set, why it's important? Even if it is in the single location, there are a lot of things that can actually change. For example, the seasons are changing, the crop cover, or even the year-to-year differences in rainfall due to climate change. All this can affect. And the idea is, can we see that from how quickly water moves through the soil? We are not going to discuss all this theory, but the idea of this video is we will see how we prepare the data, how we can prepare. And again, I'm not going to show any real data or real analysis. It's just data preparation, how we define the rainfall events, how we can start to measure the infiltration lag, all from this one data set. So let's say this is our site where we had two sensors, one at 5 centimeter and one at 50 centimeter, and both of which give me a time series of soil moisture, something like this. For every 15 minutes we have for around 10 years. 10 years, every 15 minutes we have a time series. Similarly, at 50 centimeter we have another time series, something like this. So we have this high resolution time series, and let's say we also have precipitation data collected, something like this, where we measure how much rainfall in millimeter we get. And if we want to see this rainfall when it falls at the top layer, how it moves along the soil column, and we get a response at 50 centimeter, what we have to do is that we cannot actually use all this 10-year time frame into the analysis for a meaningful answer, because the rain events are actually separated by dry periods. If you see, it rains for a while and then there is no rain and there is dry, and then again it rains and then there is a dry spell. And so these are actually events. And sometimes there are also a long dry spell before it again rains. So it's like an impulse response, the rains. And so what we have to do is that we cannot analyze entire time series at once. So I cannot cross correlate the precipitation and the soil moisture to find how much time it takes the water to move from here to here. So what I want to do is that we have to define a way to define the event, the rainfall event, and for each event we have to actually do time series analysis, so that each rain event is like an experiment. So this is like an event, and we should consider this as an event where we use this window to do any meaningful time series analysis. This is like an impulse function, and we see the soil's response by comparing the correlation between this and the precipitation, and this and the precipitation. So we have to separate first our time series into meaningful event, and that's why we need a way to define where an event begins and ends. How much rain counts as an event? So if we have just one spike for 15 minutes, it's a passing storm. It will not infiltrate deep down 50 centimeter. Maybe it will just run off, or the plants will take away, and this layer of soil will not see if there is no enough rain. And if there is overlapping events, if there is too much rain and there is too much rain for entire season, we cannot know the response, because we don't know, like the rain should be there and followed by a dry spell, and so this we can consider it as an event, and then we can see then how long it took for this water from 5 centimeter to travel down to 50 centimeter. So that's what we do when we talk about infiltration lags or time delays. So we do cross correlation or any time series analysis for each event window that we call here. And so we will see how we define this event window. So to define actually the event in the event detection, what we should do first is that we should define a way to actually quantify the rainfall threshold. So what I mean is that, let's say we have the time series of rainfall, and then we define a threshold, let's say 5 millimeter or something like 0.5 millimeter, because each impulse here means 15 minutes. We have 15-minute time series. Let's say this is our threshold of 0.5 millimeter. So one way is that what we can do is that we can define our threshold as instantaneous. So we look for periods where rainfall rate is above a minimum threshold, let's say 0.5 millimeter. Sometimes we can also define an event or a rainfall threshold by integrating rainfall over a sliding window. So like we can say, if at least 3 millimeter rainfall falls within any 1 hour, we can define it as a start of an event, or it can be instantaneous. Let's say it's 0.5 millimeter for a minimum duration. The rainfall should not be like just it occurred above the threshold for only one of the 15 minutes. It should at least last for 2-3 time steps, maybe 30 minutes or 1 hour. Then we can say there is enough water for our infiltration study, because short or weak events may not generate a real hydrological response. And so we can actually plot the histogram of event durations and see where we can define it. I mean how we can define the minimum duration. Let's say what constitutes a event. If there is 1 spike or 2 spike above the threshold, or 3 spikes, What is an event? That also we should consider. So what I mean is the minimum duration. Minimum duration, or how long the rainfall lasts. And the reason is that it filters out any tiny rainfall that doesn't matter for our infiltration study. And also we should also think about the gap separation, like usually there is rainfall and there is a gap. There is a dry spell and then again it rains. Should I merge these two as one event, or this is one and this is one? If this gap is sufficient, this gap is sufficient to qualify as the new event. So we have to define a way that how we define this gap to qualify as an event of its own. So the first idea is that we have to divide the time series into meaningful events for our time series analysis. For that we have a criteria of rainfall threshold. The rainfall has to be at least above our threshold for some minimum duration of time. It cannot be like just it was a flash flood and the cloud went away and there is no rain after that. Then it's no use for our infiltration. So it should last for at least 30 minutes or 1 hour or some duration that we have to define it. That's what I'm trying to tell here. And also the gap, we have to define a gap scientifically. For example, to split events, let's say we require a rain-free gap. If the rain resumes immediately before that definition of a gap, we should merge those two events as a single event. For example, here the gap is very low, but here the gap is much more. So this can be an event of its own, and this can be an event of its own. And so this is what we have to define: the threshold, the minimum rainfall per interval, the minimum duration of how long the rainfall lasts, and the gap separation. A dry gap is needed to separate the consecutive events. So by combining these criteria, we make sure that each event we analyze is physically meaningful for our infiltration study. That is strong enough, long enough, and isolated from all other events. And these choices should be actually based on data. Actually, we have to derive the threshold, the minimum duration, and the gap separation from our data, or it can also come from the literature. So once we actually define our rainfall event, for example, let's say this is our event, and we have defined the start and the end of the event based on the three criteria, that is the threshold, the minimum rain duration, and the gap separation. And from here, what we have to do for the next step is to determine the analysis window, like each analysis window that we will use it for the time series, like the cross correlation. For that, what we have to do is that we have to consider the soil moisture lag characteristics. Let's say this is our rainfall event, and we see that, and if we see the soil moisture at 5 centimeter, it is peaking something like this. It takes, let's say, 10 minutes to show a peak. The rainfall is reflected in the soil moisture. And the 50 centimeter, however, takes some longer time. Let's say this is the lag time. And this is the peak at 50 centimeter. So this is the driving force, the impulse driving force, and the response at 50 centimeter takes a certain lag time that we can see, and we can record that. And if we do this lag time for every valid event, if we plot a histogram or a cumulative distribution function like this, for example, in the y-axis we have number of events, the valid rainfall events, and you have the lag time, which is the response time for 50 centimeter to show its own peak. So we get some curve like this. the cumulative distribution function, and at 95th percentile you can define something called as L max, and you can also add some safety buffer like 1 hour or something like that. So this is the L max, and now with this L max we can define our analysis window something like this. Let's say our rainfall event is something like this. This is our rainfall event, and this is the beginning of our rainfall event, and this is the end of our rainfall event. What we can do is that we can have a pre-event baseline period, something like this, like 2 hours or 1 hour before the event starts. Let's say it's 2 hours, and our event has started, the rainfall has started, and it has passed all the 3 criterias. For example, it has the minimum threshold, minimum duration, and the gap separation. Everything satisfies for that to be an event. And now we take 2 hours before that, take all the time series data, and then entire rainfall event, and then the end can be till L max, which we have found out using the cumulative distribution function of all the lag, the response time of the 50th centimeter. Or it can be at the beginning of the next event, whichever is less. For example, if the next event starts somewhere here and L max is greater, then we have to take this as the analysis window. Otherwise, we can take this as the analysis window. What do we mean by analysis window is that we take this entire time series data of precipitation, soil moisture at 5 centimeter and soil moisture at 50 centimeter to compute cross correlation or any other time series technique. And if we, for this event, if we compute cross correlation, and then we get the true lag actually. This is the lag that we are looking for, that gives us the infiltration rate. So the first lag was the lag time between the rainfall and the 50th centimeter. This is the time to peak lag. But however, the cross correlation lag, from our analysis window, if we compute a cross correlation or any other time series, we get a single peak. It's a more robust statistical approach where we compare the entire rainfall time series with the entire soil moisture time series within this event window. So this is the event window we call event or analysis window. This is the rainfall event window, and this is the analysis window, which is actually an extension based on the criteria that we discussed. Cross correlation lag is useful because when soil moisture response is not a sharp single peak, but it's rather a distributed or delayed response, while we use the cross correlation to actually get a robust estimate of the delay between the rainfall and the soil moisture response at 50 centimeter and at 5 centimeter, and that will give us the infiltration rate. And that is one of the analysis that we are trying to make in our data paper, along with other analysis like we do have electrical properties. We want to do see how petrophysics or soil salinity, does it have any effect, and other things that we will cover in the follow-up video. Thank you for watching so long. See you soon in another video. Thank you.